Bismillahirrahmanirrahim. Dear students, welcome you all to the Industrial Pharmacy class. As you know, today is the class number 2 of this week. In this class, we will discuss in detail the lecture entitled Drawing and the various terminologies used in the drawing process and theories of drawing. Dear student, the main focus of this lecture is to learn about the different terminology that is widely used in the drawing process and theories of drawing. Dear student, after the completion of today's lecture, you will be able to learn about various terminologies including the free master content, abbreviated as FMC, percent lost on drawing, and percent master content, abbreviated as percent LOD and percent MC respectively. And in the second part of this lecture, we will discuss about the theories of drawing. On the completion of this lecture, you will be learn about the theories of drawing. Dear students, first of all, we would try to understand about the various terminologies used in the drawing process. One of the prominent terminology used, that is hygrometry, that is the determination of the vapor concentration and carrying capacity of the gas, that is termed as hygrometry. It is the definition of the hygrometry, and the hygrometry, the vapor concentration is determined, as well as the determination of vapor carrying capacity of gas, that is termed as hygrometer. Another terminology that is used in the drawing process, that is free master content, and it is abbreviated as FMC, which can be defined as that free master content is the quantity of water that is free to evaporate from the solid surface. If we are going to draw a solid, and a solid having the contents, that is the water, and that amount of water, if it is free to evaporate, and that will be termed as free master content. Free master content can be calculated using the formula, that is free master content is equal to total water content minus equilibrium master content. If we subtract the equilibrium master content from the total water content, then we will get the free master content, that is the quantity or the amount of water that is free to evaporate from the surface of the solid material. And this formula you can see FMC, that is the free master content, and EMC, that is the equilibrium master content. Now, what is meant by the equilibrium master content? That is abbreviated as EMC. It is the total amount of water present in the solid material which exerts a vapor pressure that is equal to the vapor pressure of the atmosphere surrounding it. Consider this diagram in which we have a solid material, a wet mass, and the wet mass having some quantity of the moisture or water content, of this moisture content having the vapor pressure that is equal to the vapor pressure surrounding that particular material. If these two vapor pressure, that is the vapor pressure of the wet mass or the wet solid, become equal to the vapor pressure surrounding this wet solid or wet mass, then in this case it is termed as equilibrium moisture content. Humidity measurement, that is the most accurate means of humidity measurement, as gravimetric method, and humidity can be also determined by taking two temperature measurement, that is the wet bulb and dry bulb thermometer. By taking the humidity of these two temperature, the simplest instrument for this purpose, that is termed as length hygrometer, and another different method for measuring humidity implies the hygrometer, and the digital hygrometer is widely used in the pharmaceutical industry in order to monitor the humidity of any environment, any area in the pharmaceutical industry. The digital hygrometer having a digital screening of the temperature, as you can see in the figure, that is on the top. You can see by the evidence from the unit, that is degree centigrade. It is understood that degree centigrade is the unit of temperature, and humidity is measured and the percentage, and having the 51 moisture content percent humidity and 19 degree centigrade, and on the left hand side at the corner, now you can see that is the time, and it is the digital hygrometer, and having the determination of the temperature and the humidity in percentage. You can see the screen. And another instrument, that is the length hygrometer, that I have told you, that is humidity can be measured by taking two temperature measurement. That is the two temperature measurement means that is the wet bulb thermometer having cloth sock, that is the wet cloth at the end of this particular wet bulb thermometer, and at the lower side you can see the dry bulb thermometer. We have to take these two readings, and the difference of these two readings is considered from the table, and that is the handle, and we rotate this handle, and we will note the wet bulb as well as the dry bulb thermometer reading, and then we will consider the difference from the chart, and by using this type of the length hygrometer, the humidity of the environment is determined. There are certain other expression of moisture in solid which is expressed on two bases. Either the moisture present in the solid material can be expressed on a wet basis or dry wet basis. On the basis of wet basis, you can see in these two formula, when total mass of wet sample in kg is put in the formula, that is the formula for the percent loss on drying or percent LOD. That is the quantity of water in the sample in kg divided by total mass of wet sample in kg, and we will multiply it by 100 because we are going to determine the percent loss on drying. For percent, we will multiply it by 100, and that is the moisture present in a solid, which is expressed on the basis of wet basis, because the total mass or total weight of wet sample is taken here, and on the other hand the percent moisture content, that is determination of the expression of the moisture present in a solid, that is on the dry wet basis, because here you can see in the formula that is mass of the dry sample is taken in the formula, and overall the mass of water in sample in both formula similar, but on wet sample or dry sample that is different. That's why we say that the moisture present in a solid can be expressed on a wet basis. If we are taking the wet basis, it means that we are going to determine the percent loss on drying, and if we are expressing it in the dry wet basis, it means that we are going to determine the percent moisture content by using this formula, that is mass of the water in sample in kg taken dividing by mass of the dry sample in kg, that is the dry weight basis of the expression of the moisture content present in a solid material, and both formula we will multiply it by 100 because we are going to determine in both the formula either the percent LOD or percent MC, that is used for the percentage. 100 is multiplied, both the values will be multiplied by 100 in order to get the percentage. Now we will consider an example that exactly we have taken a 5 gram of moist solid, that is brought constant dry weight of 3 gram. Initial weight, that is a moist solid, was that is exactly 5 gram, and we have brought it to a constant dry weight, that is 3 gram. And by putting these in the formula, you can see percent LOD on the top and percent moisture content, that is on the at the bottom of the second. If we are going to calculate the percent moisture content, that is percent MC, we will put the mass of water in sample, that is 5 minus 3, and we will take initial weight was 5, and then it is dried to 3, and we will subtract from 5 minus 3 in order to get the mass of water in sample, because initial weight that was 5 gram when the moist solid was present, and we have dried to get 3 gram. It means that 5 minus 3, that is the 2 gram, that is the water sample, and because it is dried and then it is reduced up to 2 gram, and that's why I put 5 minus 3. 5 minus 3 means that is the mass of water in sample, that 2 gram is the difference between 5 and 3, because and the moist plus the dry sample, the total weight of the sample, that is a moist solid, is 5 gram, and we will dry it and it is kept to 3. It means there is a 2%, 2 gram moisture was present in that particular solid that was moist in nature, and that's why I subtract 5 minus 3. And then we have to put the wet dry sample, and the dry sample is 3 gram, and the percent moisture content, that is the dry sample, we have to put the value of 3 multiplied by 100 in order to get the percent moisture content, and then we are taking the 66.7% moisture content, that is the expression of moisture present in the solid on the dry weight basis. If we are expressing it into the wet weight basis, then we have to use this formula, that is the percent LOD. And the percent LOD, we have to put the values, that is mass of water in sample. Again I am going to subtract 5 minus 3 in order to get the mass of water in the sample, and then we have to take it on the weight of the wet sample, that is the total weight, that is having the sum of the moisture plus the sample and dry in nature. That was the initial weight, that is a combination of the moisture plus the dry weight of the sample, that is the total weight is 5. So we have to divide it by 5 and multiply by 100 in order to get the percent LOD, and we will get the 40%. So it is clear from these formulas that we can express the moisture present in a solid material either in wet weight basis or dry weight basis. For wet weight basis, the percent LOD has the expression, and for dry weight basis, the percent moisture content is the expression for the moisture present in that particular solid. You can see the percent moisture content and the percent LOD corrected formula that we are going to express it in the percent MC and the percent LOD respectively in order to get final reading answer in the percentage. That's why I have put the percent with the percent moisture content and percentage with the LOD. Now in this part of the lecture we will discuss in detail the theories of drying. You can see on the screen and a wet solid mass. If we have a wet solid mass and when the moisture will be present and that particular solid mass that is in the wet form, and the two forms and the two stages, that is the first one is the bound moisture and the second one is unbound moisture. If we have a solid that is wet in nature, then the wetting the moisture content present in that particular solid mass that may be present in either of the two forms, either the bound moisture or the unbound moisture or the combination of both. What is meant by bound moisture? It is the minimum water or moisture that is held by the material, that is solid mass, that exerts an equilibrium vapor pressure that is less than that of the pure water at the same temperature. At the temperature of both, that is the vapor pressure and equilibrium of both, that is the pure water and that is exerted by the moisture which is existed which is kept or held by the material. Then in this case we stated says that is bound moisture. Substances containing bound water are often called, that is bound water or bound moisture containing substances are often termed as hygroscopic substances. And the second form of the moisture that may be present in a wet solid mass, that is unbound moisture. It is the total amount of water that is held by the material that exerts an equilibrium vapor pressure equal to that of the pure water at the same temperature. In the first case, the equilibrium vapor pressure was less than that that was obtained by the pure water at the same temperature, but in this case both the equilibrium vapor pressure that is exerted, it is held by the material vapor pressure is equal to that of the wet water, pure water at the same temperature. It is the total amount of water that is held by the material and the material water content exerting an equilibrium vapor pressure in both cases, but in the first case the equilibrium vapor pressure was less than that of the pure water, but in this case it is the unbound moisture, the equilibrium vapor pressure is equal to that of pure water at the same temperature. Unbound water exists mostly in the void, that is the empty spaces of the solid material. Thus in a non-hygroscopic material all the liquid is unbound water. You can see the first one that is termed as hygroscopic material and the second one is non-hygroscopic material. And the non-hygroscopic material moisture that is termed as unbound moisture, and the unbound moisture exists mostly in the voids or empty spaces of the solid. Thus in a non-hygroscopic material all the liquid is unbound water, and a hygroscopic material on the other hand, unbound moisture is the liquid and excess of the equilibrium moisture content. Measurement of the moisture in a wet solid is referred to as moisture content or MC, that is the measurement of the has a partial moisture content that can be calculated by the weight of dry sample divided by weight of water in that particular sample multiplied by 100. We can also calculate the measurement of the partial moisture content by using this formula. You can see in the figures that is a hygroscopic material and a non-hygroscopic material, and the position and the location of the water in the both cases. That is a hygroscopic material, water in the form of the fine capillaries found in cell and fiber wall and physical interaction, while in the non-hygroscopic material, water is present in the empty spaces, that is termed as void spaces, and the hygroscopic material contains bound water and the non-hygroscopic material contains unbound water, and the condition of vapor pressure of wet solid is less than the vapor pressure of the pure water, while in the second, that is a non-hygroscopic material, the vapor pressure of wet solid is equal to the vapor pressure of the water at the same temperature in both cases. That is, the vapor pressure of wet solid temperature is the same as that used for the vapor pressure of pure water, and on the other hand, in the non-hygroscopic material that containing the unbound water, that the condition is the vapor pressure of wet solid is become equal to the vapor pressure of water at the same temperature. And the theories of drying involve both heat transfer as well as mass transfer. We have detailed discussed the heat transfer and the mass transfer in the previous chapter, and the heat must be transferred to the material to be dried. If we are going to dry a material, then we will supply the heat energy, and that particular heat energy must be transferred to the material to be dried in order to supply the latent heat required for vaporization of the moisture. Recalling from a previous week's lectures in which we discussed that latent heat of vaporization is required to evaporate the material, and mass transfer is involved in the diffusion of water through the material to the evaporating surface. The process of diffusion, that is the mass transfer, that is involvement of the diffusion of water through the material to the evaporating surface, and from the evaporating surface the liquid or the water content is evaporated, and that is evaporation and the subsequent evaporation of the water from the surface, and a diffusion of the resultant vapor into the passing air stream. That's why I say that both the heat transfer as well as the mass transfer is involved in the process of drying. And how the heat transfer is involved? That is for the vaporization of the moisture, and how the mass transfer is involved, that is the diffusion of water through the material to the evaporating surface, and subsequently the transformation into the vapor state from the surface to the environment. Consider if we have a film of liquid, suppose we have a film of liquid, suppose I have a film of liquid in this box, that is just like a film. If I put it as if I have means here a layer, you can see if I have a film of liquid over this surface in the form of and I'm going to put some layers over there. If I have in this form a layer of film, and different layers over there, and I'm going to present in this diagram. If we have a film of liquid at the surface of the material, and this is the material surface that is being to be dried, and the rate of evaporation of this film that is over this material is related to the rate of heat transfer. That I'm going to increase the heat and unit time, then the rate of evaporation from conversion from the liquid to the vapor state will be increased. That's why we can put it if we have a temperature difference over there, and here temperature and this area temperature and the inner temperature that is different, and in this case the rate of evaporation of this film is related to the rate of heat transfer. The larger quantity, the more quantity of heat is transferred, the rate of evaporation will be increased. And we can put it into in the form of the equation that is designated as equation number 1. dW by d theta is equal to Q by lambda, where dW by d theta, that is a representation of the rate of evaporation and pounds of water per hour. While here in this one, that is the Q, that is the overall rate of heat transfer, that is a British thermal unit per hour, and the overall rate of heat transfer, meaning the rate of heat transfer in the form of conduction, convection and radiation, the overall rate of heat transfer supplied to this material, that is designated by small q, and lambda, that is the latent heat of vaporization of water, and the British thermal unit per pound, and latent heat of evaporation of water, vaporization of water means that is the quantity of heat supplied in order to gain by the material. In both cases, Q, it is directly proportional to the rate of heat transfer, while the lambda, that is the latent heat of vaporization of water, that is inversely proportional to the rate of heat transfer. That is equation number 1. The rate of diffusion of moisture into the air is expressed by rate of equation similar to those used for the heat transfer. As we know that in start we say that both heat transfer and mass transfer is involved in the drying process, and the first one is the representation of the rate of heat transfer. Similarly, for the equation number 1, we can also represent or express the rate of diffusion, that is from the inner side to outer side in the form of the diffusion, that is a mass transfer involvement. We can represent it in the form of equation, just like for the heat transfer we represented, that is equation number 1. We can also put the driving force as humidity differential. In this case, that is the rate of diffusion, and in the first case the rate of the heat transfer, that is the temperature differential, and temperature differential is the driving force, whereas in the heat transfer is a temperature differential, The rate of equation for this purpose can be followed as dw by d theta is equal to k dot capital A Hs minus Hg. In this case, dw by d theta is the representation for the rate of diffusion, and k dot is the coefficient of mass transfer, which is not a constant value but varies with velocity of passing a stream. And as the area of the operating surface, the more the area, the more will be the rate of diffusion, that is the rate of heat transfer, rather than the heat transfer, that is the rate of the mass transfer. And H is the absolute humidity at the evaporating surface, while Hg is the absolute humidity at passing a stream, and Hs minus Hg is the differential in the absolute humidity of the evaporating surface and the passing a stream. That is the second equation for the representation of the rate of diffusion, or in other words we can say that the rate of the mass transfer. Just like the heat transfer, we put it in the form of the equation, but remember that the driving force here is humidity differential, while in the first case, that is the temperature differential, we have put in the form of the equation, that is the equation for the rate of evaporation, the rate of the heat transfer. After initial period of adjustment, the rate of evaporation become equal to the rate of diffusion. If we constantly supplied the heat, the evaporation at one stage, the evaporation will become equal to the rate of heat, and the rate of heat transfer become equal to the rate of diffusion of vapor. And in this case, when after the initial period of adjustment the rate of evaporation becomes equal to the rate of diffusion of water and the rate of heat transfer, the constant heat supplied become equal to, if we supply heat and constantly the evaporation process occur, and in this case both the equation number 1 and equation number 2 become equal, that we can put this into dw by d theta is equal to q by lambda. That was equation number 1, and then it is equal to k dot A Hs minus Hg, that is the equation for the rate of diffusion. That's why we say that rate of diffusion and the rate of evaporation and rate of heat transfer becomes equal. If overall heat transfer, that is the Q, is expressed as sum of the rates of heat transfer by the process of conduction, as we have discussed that the different ways or methods of the heat transfer, including the conduction and convection and radiation, the summing up of the all the ways of the rates of heat transfer, and then this we can conclude from equation 3. If we put all the values of the conduction, convection and radiation in this equation, we're putting the value rather than the, instead of Q, that is the overall heat transfer, and we're putting the values of the conduction, convection and radiation, and this equation number 3 will become dw by d theta is equal to, by putting the value of conduction and convection and radiation instead of Q, that is Qc plus Qk plus Qr divided by lambda as an equation number 3, and the rest of the equation will be same, that is k dot A Hs minus Hg. Now rate of drying can be accelerated by increasing any of the individual terms in equation number 4. If we speed up the any way of the heat transfer, the rates of the heat transfer will be increased, and by this way the drying process will be, the rate of drying, that is dw by d theta, will become increased. And if we put the values of the lambda, if increasing this one, that is the inversely proportional to the dw by d theta, that is the rate of drying. In this case, while putting the values of k more the rate of drawing will be accelerated or increased, and the area provided, if it is a larger surface area provided, then the rate of drawing will be increased, and if the humidity differential is increased, in this case the rate of drying will be increased. References consulted for the compilation of this lecture, it is Lakeman and Lieberman, The Theory and Practice of Industrial Pharmacy. Third edition pages consulted over there for drawing chapter 49 to 52 pages were consulted, and the second book for consulted, that is Amy Alton, Pharmaceutics, The Science of Dosage Form Design, second edition, page number 380. And for Slang Psychometer, diagram, you can consult this link. Thank you all for your attention. Let's overview the today topic. That's what we have discussed in the today topic. You can see we discussed the different terminologies, including the psychrometry, free moisture content, the calculation of free moisture content by using the formula EMC, that is equilibrium moisture content, and the different ways of measurement of the humidity, including the most accurate method, that is a gravimetric method, and humidity can be also by using the Slang Hygrometer, that is a two temperature taking measurement. This is the simplest one. Remember that the simplest one is the Slang Hygrometer, but the most accurate and means of way weighing the measuring the humidity, that is the gravimetric method. And another one, that is the digital hygrometer, may be also employed for the humidity measurement. And the diagram of the digital hygrometer and the Slang hygrometer, and the expression of moisture in solid by two bases, either the wet bases or the dry wet bases, and the two formulas for calculation, that is % moisture content and % LOD, along with the example that having the quantity of the moist solid and then it become dry to constant weight, and then how to calculate its % moisture content and how to calculate the % LOD. And the second part we have discussed in detail the theories of drawing, and before going to the equation and that particular theories of drawing explanation, we have explained the bound moisture and unbound moisture that may be present in a wet solid mass, and what is hygroscopic material and what is non-hygroscopic material. And hygroscopic material, water is present and different form like in capillaries and parts and cell and fiber walls and physical interaction, while the non-hygroscopic material, that is water, is present in the empty spaces, and the hygroscopic material one content, that is the water content, is formed as a bound water, and on the non-hygroscopic, that is unbound water, and the condition for the vapor pressure solid, wet solid, it become less than the vapor pressure of pure water, while in the second example, that is the unbound water, that the vapor pressure of water wet solids is equal to vapor pressure of the water. And we have also explained that drying process involves not only the heat transfer but also the mass transfer, and we have also derived equation number 1 for the rate of heat transfer, equation number 2 for the rate of mass transfer, and after initial period of adjustment, when the rate of evaporation become equal to the rate of diffusion of vapor and rate of heat transfer, and thus equation number 1 becomes equal to equation number 2 by putting the values of the overall rate of heat transfer expressed in sum of rates of heat transfer by conduction, convection and radiation, by putting the value of conduction, convection, radiation instead of the Q, the question number 4. And we also discussed it, what are the different individual terms which can affect the rate of drying, that is dW by d theta, by increasing which values rate of drying will be increased. And finally, I have also told you about the references consulted for preparation of this lecture. Thank you all for your attention.